P2.2, radioactive decay. I'm sure you're all familiar with the radioactive warning sign. Here it is again. Yellow and black is the favourite colours. So in some circumstances you get nuclei that are unstable and they emit radiation in order to become more stable. So that's why you get radioactive elements. And there are three types of radiation: alpha, beta. Beta minus, there actually is another one that goes with that, which is beta plus. I'll come back to that later. And the third one is gamma. So you need to know what each of those are. So first of all, alpha. Alpha tends to be emitted by fairly large nuclei. So the one in this picture is plutonium in this side. It's emitting an alpha particle and turning into uranium. Basically it's becoming smaller by doing that, so it spits out this little stable packet of 2 neutrons and 2 protons, which is actually a helium nucleus. So the way it's written is He for helium, 2 protons, but 4 nucleons in total, so 2 protons and 2 neutrons. So that's the standard way of writing an alpha particle, helium 4-2. And if we actually write an equation representing that, we start off with the plutonium, which, as you can see in the diagram, has got 94 protons, 240 nucleons. If it decays by alpha emission, we can write it as either alpha or He for the helium. Either is fine, both mean the same thing. We put in the numbers for that, 4 at the top, 2 at the bottom, and then all you have to remember is that the numbers must add up on both sides. So we started off with 240 here. We've got 4 over here in the alpha particle. So this number here must add up with the 4 to make the 240 that we started off with originally. So we get 240 is 236 plus 4. So that makes sense. At the bottom the numbers must add up as well. So we started off with 94 protons. We lost 2 of them in the alpha particle, and therefore what must be left is 92. So if, for example, we knew that plutonium decayed by alpha emission, we could write down those 2 bits. We would then know that the missing number here is 92, because 94 minus 2 makes 92. And if we didn't know what the element was that it decayed into, we could look it up in a periodic table and discover that it is indeed uranium. And the number at the top tells you which isotope of uranium you've got. So, in summary, that's an important thing to remember, is how to write an alpha particle in an equation. So either alpha 4-2 or He up here 4-2, doesn't matter which one. Beta is also given out by an unstable nucleus. In this example we've got radium emitting a beta particle and turning into actinium. You don't have to know all the names off by heart, but a few might be useful. So the beta particle is a special way of writing that as well. It's an electron, so it's written as an E, but it's written with a 0 at the top, meaning it's not a nucleon, and a -1 at the bottom. So it's a bit weird, this one. It's an electron from the nucleus. The problem with that is there aren't any electrons in the nucleus, and that's because it is caused by the fact that a neutron decays into a proton in the nucleus. In fact, it decays into a proton plus the electron. The electron can't stay there because the electrons can't exist in the nucleus. So it's the nucleus gains a proton and spits out the electron. Now, if we start off with radium and it had 88 protons, it also had 228 nucleons altogether. So when one of the neutrons turns into a proton, we still have the same number of nucleons. That hasn't changed, but we've gained a proton. Now, the numbers must still add up. So on this side, 88 is equal to 89, and logically this must be a -1. That seems a bit strange, but if you think of it this way, by leaving the nucleus, the electron has added a proton. So the signs are a little bit odd, but that then works. Okay, so when you want to draw a beta particle, you can either use the symbol beta or an E, standing for electron, but the numbers must be 0 at the top, no nucleons, and -1 at the bottom. Okay, so top numbers add up, bottom numbers add up, and that's the numbers you need to remember to be able to use them in equations for beta decay. There's also a hidden particle thrown out, and this is the symbol for a neutrino. In fact, this one is an antineutrino. Antiparticles are represented with a bar over the top of them. So the Greek symbol is actually a nu. It's written as a sort of curly V, and we'll come back to neutrinos later. The third type of radiation is gamma. Gamma is not a particle, that's the important thing to remember about it. It's an electromagnetic radiation, a wave. So it has no mass and no charge. So we don't need to remember anything when we write equations for that. It's just gamma radiation. In fact, you won't be expected to write an equation representing gamma decay.